it would be the same. So you will be given the block diagram that you need to implement. So if you can see here, there are two blocks. One is the D flip-flop and the other is, can you guys see my PDF?
Yeah, we
Yeah,
can.
yeah, we can.
Uh, okay, great. Yeah. So yeah, you guys, in this lab, we are implementing the 7-segment display. I hope everyone knows the 7-segment display. So yeah, for this 7-segment display, the design is having two blocks. One is the D flip-flop, which is like storing the state, your current state, and one is the counter, which gives you what state you require next. So the functionality is the current state is stored in the D flip-flop, and whenever you have the U value as 1, the counter increments the current state and gives the feedback signal as the next state to the D flip-flop. Yeah, the counter is just incrementing and decrementing the values. The D flip-flop is just storing the values. So this is the basic functionality. As you can see, there is a state diagram for this problem. So the state diagram has 6 states. Because we are like trying to implement only from displaying 0 to 5. So 0, 1, 2, 3, 4, and 5. So for each of those states, we have the state, like the one state in the state diagram. So initially, let's say you have the clear signal here. So when you clear the signal in the D flip-flop, so the state will go to 0. So whenever you are clearing, you are starting from the state 0. So let's say you are at state 0, and when you have the value, the input value U is incrementing, then you will go to next state. If the U value is getting decremented, then you go to the previous state. So that's how the state this functionality works. So from state 0 you go to 1 and then 2 and then 3 and then 4 and then 5. So when you are at state 0, you have to display value 0 in the 7-segment display. So if you can see, there are labels for each of this display. So this is yeah, for 0 you have to make A, B, C, D, E, and F values to be on. So if you can read here in the uh, description of the problem that is given, they are saying that the control signal, the 7-segment display is active low. So what does active low mean? So active low means whenever the input value given to this A as 0, then it will glow. If it is 1, then it will be off. So for the 0, you have to make A, B, C, D, E, F as zeros and G as 1. So to display the value 0. For 1, you have to make B and C as zeros and all the remaining values as 1, so that this will get displayed. I hope you understood the active low part and the block diagram. Do you guys have any questions about the block diagram or the state diagram? After this, we are going over the like the code, how you have to write code for the design that is given like this. So you will be following the same in the rest of your lab. So you will be given this design and the description of the problem like this. You have to read that and write the Verilog code uh, that we are going to see next. So before that, do you guys have any questions about the design part of this?
Is there a PDF for Lab Zero?
Okay. So when you go to lab 0, so there is this zip folder for the lab. This is for the Vivado version and this is for the Quartus version. So when you download it and unzip the folder, it looks like this. And the PDF file is inside the zip folder.
Yep, I got it. Thank you.
Yeah. Any other question? Okay, so if you guys have no questions, then we'll move forward to how you have to write, like implement this design. If you can remember from the last class, I have told you how to create the project. If you guys have any questions about how to create the project, you can ask me now or like at the end, whenever you feel like. I'm not going over how to create the project in the Vivado, but I will like explain how you have to design this uh, 7 segment display in Verilog. Yeah, you guys can see my Vivado, right?
Yep.
Okay. Okay, so when you are implementing the design that is given to you, first thing you have to remember is you have two different kind of source files. One is the design source and other is the simulation sources. So simulation sources and design sources, both you are supposed to write. Simulation source is nothing but writing the test bench to test the code that you have written in the design sources. And design sources are nothing but the design that you have in this folder. So if you can see, you have two blocks, D flip-flop and counter. So that's why I have two modules in the Verilog. So here we have written both the modules in the same file. So if you can, like, I will just minimize all the other unrequired parts so that you can see better. Yep. Yeah. So if you can see here, in this we have written both the D flip-flop and counter in the same file. But if you are like comfortable writing the different blocks in the different .v files, that is also fine. Um, yeah, so that's how you need to write the design file. So in the design file, you have two modules, right? The D flip-flop and the counter. So first, let's go over how we have converted this D flip-flop into the Verilog code that we have here. So here, if you can see in the D flip-flop, you have three inputs and one output. So one input is next state, one input is clear, and one input is clock. Excuse me. So yeah, so if you see here, you have three inputs here and one output, the Q value. So one thing you have to always remember is the outputs when you are writing in the Verilog, the outputs always need to be registers in the design sources. So why is it so? So in the register means you are storing the value. So output values you have to store before you read in the Verilog. So that's why all the outputs need to be specified as registers. If you don't specify anything, it would be like wire, so which doesn't store any values. So all these inputs we are giving from the test bench and we are storing it there. So that's why we don't need to store it here. But outputs you have to read into the test bench, and there you don't store outputs, so you have to store it here. So yeah, so outputs you need to always specify as registers. And when you are representing a vector, you have to represent in this way. So this vector is of 3-bit size because you have 6 states, and to represent 6 states you need 3 bits. With 2 bits you can represent 4 states only. So yeah, with since you have 6 states, you need 3 bits to represent. So that's why the state has 3 bits, 0, 1, 2, and 3 bits to represent the state value. And yeah, the clear and the clock signal. So, and when you are writing the conditional statements, except the assign statement, all other code that you write in Verilog should be in the always block. And the always block has a constraints list. So what does the constraint mean is whenever the value that is mentioned here changes, then only the code inside this always will block will get executed. So here you have mentioned the D flip-flop value here in this module. You want it to change only on the clock cycle, only on the positive edge of the clock cycle. So that's why in the constraints list, you have mentioned that whenever there is a positive edge of the clock, so you have to execute this code. So yeah, so whenever there is a positive edge of the clock, the value in the D flip-flop changes. Right. So you have the clear signal whenever the uh, here the clear signal is active low signal. What does that mean? So whenever the clear signal value is 0, that means you are clearing the D flip-flop. And whenever it is 1, the D flip-flop will function normally. So that's what is mentioned here. Whenever the clear signal is 1, you will just give the output value same as the input value. So if you see here in the block diagram, the output is Q and the input is next state. So yeah, so whenever the clear signal value is 1, you will give the output value same as the input value. Otherwise, when the clear signal is 0, that means you have to clear the D flip-flop. So whenever the clear is 1, it goes to the else statement and you are giving the value as zeros. And one more thing you have to remember in the Verilog code is that the difference between the blocking statements and the non-blocking statements. So the here you are block. What does the blocking statement means is the value of this output will get assigned to the input at the end, like when you come here to the end of the always block. So when you write it like equal to, so this get assigned immediately. That means whenever this line completes its execution, the value of Q would be NS. When the value is less than or equal to, the value of Q will become NS at this statement after executing this end statement. So that is the difference between blocking and non-blocking. So according to your design, you have to assign the values. You have to write whether it's blocking or non-blocking. Yeah, so that's how you implement the D flip-flop. The design of the D flip-flop is very simple. Um, yeah, any questions about the D flip-flop implementation from this block diagram? So the main things you need to remember is what are the inputs and what are the outputs and how on each input the output is changing. So here the inputs are next state, clear and clock. Output is Q and the output is changing on the clear signal or on the positive edge of the signal. And here if you can see, the clear is synchronous with the clock. That means you are not clearing the value, you are not clearing the D flip-flop asynchronously. That means whenever there is positive edge of the clock and the value of clear is 0, then only you are clearing the D flip-flop. So this is called a synchronous way of designing uh, the module that is given here. Yeah, that's what is the D flip-flop implementation. Um, any questions about this?
What is the three apostrophe B000 again in that line you're
Okay,
on?
yeah, sure. So as I mentioned, the Q value, and this is like 3-bit, right? So you are mentioning the 3-bit value and B is binary representation. So the next 3 bits 000 will be getting assigned to Q. So whenever you are assigning a fixed value, you have to write it in this way. Either if you write in the decimal way, like 3D0. So D means decimal and B is binary. So when you are writing in the binary, you have to write all the bits. Let's say 3 bits here. And when you are writing in the decimal, you can say 0. So let's suppose you are representing 5. you have to write q is less than or equal to, if you are writing in 3b, you have to write 101, sorry. And if you are writing in the decimal, you have to write 3d5. Yeah. And there is this hexadecimal representation also. For that, you have to write h. So this number represents how many bits you have, and this represents the way you are representing the value that is coming next. Yeah. So that's what is the
That makes
difference
sense.
here.
Thank you.
Yeah.
Quick question with that. Do
Sure.
we have to write all the binary values for it, or since it's in an if statement, it's just going to go to the next state and keep on going?
Sorry, I didn't get. Can you repeat it again?
What I was saying, can you hear me?
Yeah.
What I was saying is that do we have to write all the binary states, or like do they, since it's in an if statement, it will just automatically go to the next state?
Okay. So the state
Like you
diagram.
see how you write 000. Do we have to write, like in the state diagram we have the binary number 000, but like do we also have to write q is less than or equal to 3-bit binary of 001, or does it, since it's an if statement, it will just go to the
Sure.
next state?
I got it. So this implementation here is just for the D flip-flop, this module. And this state diagram we are mentioning in this like counter, right? So when you go to the counter, so whenever you have the U value, the input of U is to the counter. So this state diagram, transitioning between the states, we will write it in the counter module now.
Okay, that makes sense. Thank you.
Yeah. Yeah. Any other questions? Okay, so if there are no questions, then we'll move on to the counter implementation. So as I mentioned, it is an up-down counter. That means you can either increment the value or decrement the value present in the counter, like the input value that is given. Yeah, so when the value of u is 1, you are incrementing the counter value. And when the value of u is 0, you are decrementing the counter value. So if you can see, if we follow the same design that we have used for this. So what are the inputs to this counter? Can anyone tell me what are the inputs to the counter?
U and Q, which is the
Yeah,
3 bits.
yeah, that's correct. So we have two inputs. So you have to mention two inputs here. You have two inputs here, one and the input U. And the outputs here are, can anyone tell me what are the outputs here?
The next state and the LED display.
The next state and
The LED displays. So A
yeah,
to G.
yeah, that's correct. So we have 8 these things and one of the next state. So you have to represent all the outputs here, next state and A to G. As I mentioned, you have to represent outputs as registers here. Yeah. And now since we have represented the inputs and outputs in the module, the first step is done. And the second step is you have to understand what is the logic and how the outputs are changing based on the input values. So you will take the input value and the value of U, and based on the value of U, you will change the NS value here, right? So here in the constraint list, um, generally we have to write only the input values. So this constraint list says on which inputs you have to change the output. So here you have to change the output even if one of the two inputs changes. So if the value of Q is changing, then you have to change the next state value, or if value of U is changing, then you have to change the next state value, right? So yeah, so you have, if you say at asterisk like the star here, that means on all the input values, this code will be executed. So yeah, so we have two inputs. So instead of writing q comma u in the constraint list, we can write asterisk, which says that on all inputs, this code will be executed. So and one thing you have to remember is to write, so the general code is whenever you are in the current state, the next state will be q plus 1. So that when u is equal to 1, ns is q plus 1. When u is equal to 0, ns is equal to q minus 1. But there are two base conditions here. So whenever you are at the state 0 and u is 0, you cannot do q minus 1. Instead, you have to make q as 5. Sorry, next state as 5 when q is 0. And in the similar manner, when the value of next state like q is 5 and the next state value should be 0. So there you can't write q plus 1. So those are the two base conditions you need to mention explicitly. So that's what we are writing here. So if u is 1 and if the q value is 5, you have to make the next state to 0 instead of q plus 1, which is 6. Otherwise, for all other states, you can just directly write q plus 1.
I have a
And in
random
the,
I have a
yeah,
random question. It's gonna
sure.
sound stupid, but if you do +1 or -1, that increments and decrements it. It doesn't worry about like whether it's binary, hexadecimal, or decimal, right?
Yeah, it just increments by 1.
Okay,
You don't
thank
need
you.
to. Yeah, yeah. Yeah. Any other question? Okay. Yeah. So this is the first base condition, and the second is if u is 0. So you are coming into the else statement. So if q is 0, that means you are in the zeroth state, then you can't do q minus 1 when u is 0. You have to make it 5. So that is what is happening here. Otherwise, you are making it as q minus 1. Yeah, this is for the one input you have here, the ns input, but you have to give this a to g inputs as well, like outputs as well. So for that you are giving the case statement here. Like you can write the if else conditions also, but when you write the case statement, it looks a little bit neater in the code. But if you are comfortable using the if conditions, you can use that as well. So okay, how the case condition works, I think everyone knows it, but I'll explain it again. So whenever this is the input that you are giving as the case, so here we have to give the input q, and this is the value for each of the case condition. So if the q value is 0, this code will be executed. If the q value is 1, this code will be executed, and so on. So since you have 6 states here, you have 6 conditions here. When it is 0 except g, all other inputs should be 0. And one other thing you have to remember in Verilog is for all the things that you write, like you have to write the begin and end. For the case statement, you have to write begin and end, and the always condition, you have to write begin and end. And for the if condition also, you have to write begin and end. Yeah, so when it is 0, the value of g is 1 and all others are zeros. And when it is 1 except c and b, if you can see here, except b and c, everything else should be 0. So that's how these conditions are being written for the other outputs that we have in the counter module. Yeah, and then you have to write the end case and these end uh, things for the begin statements that you have written here. So yeah, that's how you will implement the counter module. So we have finished implementing this complete diagram that you need for the 7-segment display to work in the Verilog. After that, we have to write the test bench, and then we have to check our code. So before going on to how to write the test bench, any questions about the design?
Another question. When
Sure.
does like the case code like runs?
Yeah, so when you are writing the case statement inside the always block, right?
Yeah.
So whenever you come inside the always block, the case statement will run.
Okay, gotcha. Okay, that makes sense.
Yeah, yeah. Okay, so let's just go to the test bench. Yeah. In the test bench, in the module, you don't need any of the inputs or outputs. And like you will consider this entire thing as one single black box. So you will consider these two modules as one unit, and then you will write the test bench. And whatever are the inputs to these things, like these uh, clear, clock, and U, which are coming from outside, are written as the registers, and the outputs that you have from this are written as wires. And you need to represent this connection and this connection between the two modules, so you need two other wires here. Right. And how you instantiate. So in the test bench, you have to instantiate your design modules, and you have to mention how they are interconnected with each other. So here you have two design sources. One is D flip-flop and another is counter. And you have to instantiate two modules. When you are instantiating, the first thing you have to write here is the name of the module that you have given in the design source. So when you go to the design source, here the module name is DFF3. So this you need to write here DFF3, and this is the variable name that you are giving inside this test bench. So you can give any random value, but it would be better to look the code if you write this name underscore test bench. You are saying this is the test bench module that you are using. Yeah, this is the name in the test bench, and this is the name that you have to write from the module design source files. And the order in which you need to write these are the order in which you have defined this. And there is one other representation of how you have to write in the inside this module, like inside this parenthesis, but I'm not going over that because throughout this labs we will be using this convention of writing in the order that we have mentioned here in the design. So if you see here, first it is ns, and then clear, clock, and then q. So if you see here, you are writing ns here, clear, clock, and then q. Similarly, for the counter module, you have to write the name as counter and the test bench name here and the order of the signals that you are using in the counter. Yeah, if you see here, the connections between these two modules are Q and NS, right? So when you see here, the Q here is there and it is given as input here. And the NS here we have, and the same signal you are using here. So you have to like keep in mind this block diagram, and like you have to connect it accordingly, these things. Yeah, so this is about the instantiation of the modules, the design modules that you have written in the design sources. And so there are two things that you will write here in the test bench. One is the initial module and other is the always module. So always module will run like multiple times but the initial block, when you mention initial, so initial, whatever you write inside the initial will execute only once when you run the code. So initially you are making the clear signal as 0, and then you are making the clock as 1, and you are giving u value as 1. And here when you mention hash 1, that means 1 nanosecond time. After 1 nanosecond time, you are making the clear signal as 1. So initially you have written clear as 0, and after 1 nanosecond, you are making it as 1. So how do you know this is 1 nanosecond? We will mention the time scale here. So for all the labs, you will use this same time scale, 1 nanosecond. So that's how you know this is 1 nanosecond representation. And when you write 16, this is called 16 nanoseconds. So after 16 nanoseconds, you are making the value of u to be 0. And so after every clock cycle, you have to toggle the clock, right? From 0 to 1, 1, 0, 1, 0. So for that one, you can write it like this. So inside the always block, you have to mention 1 clock cycle, and then you have to toggle the clock after every 1 nanosecond. Yeah, so that's about it. So when you change the clock, this here the value of this will change, and internally the q value will be assigned to ns, and that value is given to the counter, and that counter will change. Sorry, this ns is given like the q input, and from the q input the values of all these things change in the counter module, and the functionality that you have intended when you before writing will be completed here.
Sorry, but do you mind going over this again? Like the initial and
Sure,
the all part?
sure.
Thank you.
Yeah, so in the initial block, so the initial block, whatever the code that you will write will be executed once. So what you need to check, initially we have to make the clear signal as 0, because we will clear off everything that is present till now. And after clearing it off, then we have to make the clear signal as 1, right? Because if it is 0, every clock cycle you change, that will be 0. There will not be any changes in the states. So for that functionality, you are making the clock clear signal as 0, and then you are making the clear signal as 1. So these two things you need only once, like you need these things to be happen only once. So when you write in the initial block, so it will happen only once. If you are writing in the always block, it will like keep on happening till you finish the execution of the program. So
In
yeah,
the
and
initial,
sorry, yeah, go ahead.
in the initial block, what is
Mhm.
hashtag one? You said it was 1 nanosecond. So what does that
Yeah,
mean? Like hashtag one, and then that's the whole statement. So does that mean after 1 second initiate the always block?
yeah. After 1 second of your execution starts, then clear. So this will. So let me just run this and then show you the waveform, so it'll be easier. Yeah. So when you see the waveform, so the clear bit, if you can see here, so initially at the start it is 0 because you have mentioned it as 0, and this 1 nanosecond, after 1 nanosecond, here you have 1 nanosecond, here you have 1 nanosecond. So at this point of time it is becoming 1. So that's what is mentioned here in the test bench. And initially the clock value is 1, and you are changing it on every 1 second, right? Excuse me.
Okay, so the part in the always block, that means change it
Mhm.
every 1 second. Like toggle the clock every
E-
1 second. That's what it means.
Every 1 nanosecond. Yeah. The
Every one
time
nano.
scale is,
Yeah.
yeah.
Right.
So after every 1 nanosecond, it's toggling, right? So
Okay.
the
Got it.
clock value is changed. Yeah.
Got it. Thank you.
Yeah. And initially you are making U as 1. So if you see in the clock cycle, initially the U value is 1. And after 16 nanoseconds, the U value you are making it as 0. So that's how it becomes 0 here. Yeah, so all the one-time tasks that you need in your code will be written in the initial block, and whatever things you repeat it over the period of time will be written in always block. So in general, so the only thing you write inside the test bench in always block is the clock, and all other signals you usually mention it in the initial block, the functionality. Yeah, so that's how you need to write the test bench, and when you run the simulation, you will get the values accordingly. So if you see here, in the initial, when the clear value is 0, so the Q value should be 0, right? So you have to clear out the thing present in the D flip-flop. And the counter module doesn't depend on any of the clocks. So it will increment by 1 because the U value is 1 here. And if it is 1, so the next state you will get here in the D flip-flop is 1. And it is happening on the positive edge of the clock. Excuse me. So the values here are changing on the positive edge of the clock, if you can observe that. So for the initial some amount of time, like 16 nanosecond, since U is 1, you are incrementing the counter value. So it is becoming 0, 1, 2, 3, 4, 5, and 0 again, and 1, 2 here. And after 16 nanoseconds, if you can see here, it is on the negative edge of the clock. So that shouldn't affect the D flip-flop value till the positive edge of the clock. So the 2 has remained for this one negative clock cycle, and whenever it is 1, so the clock is on the positive edge of the clock, positive edge, the value of the counter is decrementing. So it is becoming 2 to 1 on the positive edge. So since U is 0, it has to decrement. And from 0 to, it has to go to 5, and then 4, 3, 2, 1, like that. So the functionality is happening in whatever way we want.
I have a question.
Sure.
So, where cursor is right now, like where the yellow line is, right
Yeah.
before the next state is 3, and after that, the next state is 1. But then
Yeah.
when we actually see the Q value, it's after 2, it's 1. So, what is happening
Hmm.
there? Like, there are multiple
Yeah.
transitions in the next.
Yeah. Good question. So when you see the counter here, the counter is not depending on the clock. So it will depend only on the changes of Q and U, right? So whenever U is changing, here in the D flip-flop, like in the counter module, you have written on every change the values of outputs, right? For the counter. So when U is becoming 0 here, the counter should change. So the input to the D flip-flop is changing, but the output will not change because it is on the negative edge. So it will change only on the positive edge. So here the counter is not on the clock. So the transition happens whenever one of these value changes. But this D flip-flop will change only on the positive edge of the clock. So that
Got it.
is what is happening here. Yeah. Yeah, so that's how you write the code and you verify the code. And there is one other feature that you can use in Vivado is resetting your simulation. So when you reset your simulation, you don't have anything on the waveform. And you can give the time frame till how much time you want it to be run. So when I have given here 2 nanoseconds, so when I run for the first time, only 2 nanoseconds of the waveform will appear. And when I run it again, I will get 2 more nanoseconds. So on each, like on each of this time frame, what is happening in the signals, you will get the output value here. And like you can use it for the debugging as such, but for the lab submission, you have to like submit the entire waveform that you are getting here. Yeah, so that's how we implement the design into the Verilog code, and yeah, that's how you debug your code. Any questions about that? Okay, so when you if you don't have any questions, I'll go over what you need to submit for the lab folder, like the report. If you see here, every lab contains the explanation of what you need to submit for the report. So here it is mentioned your Verilog code and design and both test bench. So that means you have to, whatever you have written in this, so entire thing you need to copy and paste into your report, and the test bench code you have to copy and paste into the report. After that, it says the waveforms. So the waveform here is this thing. So at least you have to show 2 or 3 transitions, like what is happening here. And you have to take the screenshot of this and like put it in your report. And next it says schematics, IO planning, and floor planning. So what are those? I mentioned in the last class, but again, I'll mention it here. So after simulation, you have to run the synthesis. So you have to run the synthesis. And once you run the synthesis, like synthesis takes a little bit of time. So once you run the synthesis, you will have the schematic, IO planning, and floor planning. And after running the synthesis, you have to run the implementation as well for your code. So I'll show the 3 things that you need to put it in your report once it gets finished running. But during this time, you can ask like if you have any questions.
Why did you change U10 test bench specifically after 16 nanoseconds?
So here there is no specific reason why I changed after 16 nanoseconds, but I just wanted to show, even though these changes, this will not change. So I just gave after 16 nanoseconds, but there is no specific reason as such. I just wanted to show the transitions in both the states when U is 1 and U is 0. So that's why.
Okay, yeah, that makes sense.
Yeah, so synthesis is completed. So when the synthesis is complete, you will get the schematic. So when you will get this thing highlighted here, when you open this, expand this, so you will have the schematic here. When you press it, it will get like opened up here. Yeah, so this is the schematic. This also you need to take the screenshot and then put it in your report. And when you drop down here, you will have IO planning. And this is the IO planning. This also you need to put it in your report. And when you go to floor planning, you will get the floor planning also. And this also you need to take the screenshot and put it in your design. So things that you need to put in your report are the code and the waveform, the schematic, the floor planning, and the IO planning. And you have to run the implementation also. Like after implementing, you will get this folder opened up. And if you can, like, you can put anything from the synthesis or implementation in your report, but at least one of that you have to run it. Yeah, so these are all the things that you need to put it in your report. And one other thing to remember, important thing is, when you are, after you write the report, when you create the project in your Vivado, all these things will be created in the folder that you have created, and you have to zip it up, all these things. So when you go into the so you have to zip this entire folder and then submit it. So you cannot select only this folder or only this folder and then submit it. You have to zip entire folder which is created through your Vivado, and then you have to submit it, because we will run your code again and re-verify whether whatever is written in your report is like matching or not. So we will definitely run your code. So to run your code, we need all these things. And if we cannot run your code, you will not get points for the report as well. So be careful about submission. You have to submit the entire folder. So that's about it. That's about the lab 0 explanation. In the next class, we will look at lab 1. And in the lab 1, you have to do the divider. So I think in your 270 class, you might have studied about the divider. So just go over the lab 1 PDF that is given and try implementing it. But we will discuss just the design part, not the code implementation part for lab 1. That is your part. So the design part we will discuss in the next class. But yeah, you can go over and start writing your code, because you know now how to write your design and the simulation files. Yeah. So that's about it for this class. I will take any questions if you have. Yeah. So that's about it.
I have a quick question.
Sure.
So, for the report, do we like
Mm-hmm.
do the report on like say like Word and then just put the Word file
Yeah.
in the
Yeah.
folder?
You can submit the Word folder, Word file or the PDF file. Uh, but generally we would prefer PDF file, but Word also works.
Okay, yeah. So we put the PDF file in the folder, right? And then we submit, and then we zip the folder, or do we just is it a separate submission?
Uh, no, you will put the PDF file in the folder and then zip it and then submit the folder.
Okay, thank you.
Yeah. Any other questions?
Hi, I have a question.
Sure.
Do we need to submit anything for lab 0?
No, nothing. Lab 0 is for your reference, and we are explaining lab 0 because you will understand how to convert the design PDF that is given to you into the Verilog. You don't need to submit anything for lab 0.
Okay, thank you.
Yeah. Any other questions?
Can you just go how you open the synthesized design again, and what do we like have to do again? So we got
Sure.
like
Yeah, for running the synthesis, you have to click this one, and once you run it, this will get highlighted. Otherwise, it will be like this unhighlighted part, so you won't get anything here. So once your synthesize is completed, then you will open it, and then if you scroll down, there is a schematic here, and when you click it, this will be opened, and you have to take the screenshot of this. And after that, when you go here to the extreme right and drop down here, you'll have the IO planning, and you will get here this one. And when you put the floor planning, you will get this one. So yeah, these are the 3 things that you need to submit.
okay, thank you.
Yeah. Any other questions? If you have any questions, feel free to email any one of us or attend office hours. Uh, yeah, so that's all I have for today's class. If there are no questions, then all of you have a great weekend. See you in the next recitation section. I'll just hang in here for a minute so that if anyone have any questions, you can ask me. Yeah. So if there are no questions, then See you all in the next class.